Hello everyone, my name is Chris Edwards, and today we are going to write a SQL query. Our problem today is probably familiar to many of you as a common toy problem for traditional programming languages like Python or JavaScript, but today we're going to have a go at it in SQL. The Fibonacci sequence is a sequence of numbers in which each element is the sum of the two elements that precede it. In the most common version of the sequence, the first two numbers are defined to be 0 and 1, and the rest of the sequence follows like so. 0, 1, then 0 plus 1 equals 1, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, and so on. And so today, we want to write a SQL query that generates the first n Fibonacci numbers, ordered from smallest to largest. And just to make it clear, I'm not expecting a stored procedure or database function or something like that that actually takes n as a parameter. We're just going to be writing a regular select statement that has a hard-coded number somewhere in there that represents n, such that changing that number directly informs how many Fibonacci numbers the query returns. For example, setting that number to 15 should make the query return the first 15 Fibonacci numbers pictured below in this expected result list. And that's all the setup for today. If you want to have a crack at solving this problem yourself, there are links in the video description to this full problem statement and instructions on how to replicate this coding environment on your local machine. Feel free to pause the video now and come back later for a solution walkthrough coming right up. All right, welcome back everyone. We will now take a look at a possible solution to this problem. So the first thing to recognize about the structure of the Fibonacci sequence is that it is recursive. The nth Fibonacci number is defined as the sum of the previous two. This is a recursive definition that requires you to compute previous items in the sequence in order to compute later items in the sequence. And this is therefore a perfect candidate for a recursive SQL query. So first, a little review on how recursion works. In general, you have two main elements, the base case and the recurrence relation. The recurrence relation part tells you how later members of the sequence are defined or derived from earlier members of the sequence. For Fibonacci numbers, the recurrence relation is the rule that each number in the sequence is the sum of the previous two numbers in the sequence. However, the recurrence relation is not sufficient by itself to fully define a sequence because we need a way to get the sequence going in the first place. Defining the next member of the sequence in terms of the previous members is all well and good if you have previous members to work with, but how does the whole thing start? That's where the base case comes in. The base case is just a brute fact of sorts defining the beginning of the sequence. For a sequence like Fibonacci, where each element depends on the previous two elements before it, we need a base case that defines at least the first two elements of the sequence so that the recurrence relation has everything it needs to take things from there. And our problem definition today gives us that base case. The standard form of Fibonacci defines the first two elements to be 0 and 1. So we have our base case and the logic for our recurrence relation. Now, how do we translate that into SQL? Well, the general form of a recursive SQL query looks something like the following. We have a with clause, also called a common table expression or CTE, with the special recursive keyword in its definition. Now that CTE is made up of two unioned parts, a non-recursive query that effectively acts as our base case, and a recursive query that references the CTE itself. You see here, it's selecting from the recursive CTE that it is itself a part of. And it's in this recursive part of the union where we define our recurrence relation. The base case is usually a select query that pulls a limited set of data from some existing table, and the recurrence relation will often, but not always, join back to that same existing table from the recursive CTE itself. But it works, a little bit differently depending on what problem you're actually solving in the moment. Just to drive this structure home, let's look at a simple concrete example based on some code from the PostgreSQL doc pages. Let me just paste this in 1 sec here. Here we go. And we'll run it here so we can have the results handy. Now, as you can see, this query recursively generates all of the integers from 1 to 100. And in this case, the base case is just the number 1, defined here using a values clause. And the recurrence relation is the simple fact that each positive integer is 1 more than the previous positive integer. More specifically, the recursive part of this recursive CTE is selecting the previously generated integer in the sequence n and adding 1 to it to produce the next integer in the sequence. And it keeps doing this as long as the previously generated integer is less than 100. The final loop of this recursion will happen when n here is 99, and then 99 plus 1 is 100, so the final row produced by the query will contain the number 100. Now this query right here, generating the first 100 positive integers, is actually a decent starting point for constructing our Fibonacci query. There are 3 main differences between this query and the query that we want that can generate the first n Fibonacci numbers. First difference is that the base case in this query is just the number 1, but the base case for Fibonacci has 2 numbers, 0 and 1. The second difference is the recurrence relation for Fibonacci references the previous 2 numbers in the sequence, not just the previous number like this one does. And the third main difference is that the stop conditions for these queries are subtly different. You could say that this query generates either the first 100 positive integers or all positive integers less than or equal to 100. Now, these happen to be equivalent statements because the quote-unquote index of the positive integers is equal to the value of the integers. For example, the 10th positive integer is the number 10, the 55th positive integer is the number 55, and so on. This is not the case with the Fibonacci sequence. The nth Fibonacci number is not the literal value n. In fact, the value of each successive Fibonacci number quickly gets a whole lot bigger than the index of the number, in other words, which position in the sequence it occupies. For example, the 10th Fibonacci number in this list over here is 34, the 15th is 377, and so on. And for our purposes today, we want our Fibonacci query to stop based on the index of the number, not the value of the number, the nth Fibonacci number, not the Fibonacci number less than or equal to n. So, now that we have identified the differences between this query and the query we want, let's write some code. First of all, let's fix our base case to have both 0 and 1. And let's update the CTE definition accordingly. I'm going to call this previous n and n. Okay, now let's try to fix the recurrence relation. In order to provide the necessary inputs for the next iteration of the recursion and to make sure that this side of the union all lines up with the base case column-wise, we need to calculate values for both previous n and n in the recurrence relation query. So to accomplish that, the old n becomes the new previous n. And we get the new n by adding the old n and previous n together, like so. It's like we are shifting a window, looking at the sequence, shifting it over by 1. So like, let's say our previous n is 5 and our n is 8. On the next run of the recursion, we're going to shift over by 1. So now the new n is 5 plus 8 equals 13, and the new previous n becomes 8. So our window's kind of shifted from here to here, and then it'll keep going, shifting to here, and so on. Okay, we've addressed the base case and the recurrence relation. Now we just need to tell this query how to stop after the nth Fibonacci number. We need to update this where clause somehow. But currently, we actually don't have the right information available for the where clause to filter on. Remember, we essentially need to filter on the index of the Fibonacci numbers, in other words, what position in the sequence the number has. Right now, all we have to filter on are the values in the sequence, the n's, previous n's, etc., and those don't help us here. So we essentially need to introduce another column that can track the sequence index for us. And just like with the values of the sequence, we need to define a base case and a recurrence relation for this index. So what is the base case of an index? Well, it depends on whether you are following 1 indexing or 0 indexing, for starters. And for simplicity's sake, I'm going to go with 1 indexing for now, so that we can say the first Fibonacci number is 0, the second Fibonacci number is 1, and so on. So we just add an index column to the CTE definition here. And now for the base case, since we are using 0 for previous n and 1 for n, it seems fair to tie the base case index to the 1 rather than to the 0. And since 1 is the second number in our sequence, our base case index in this context is going to be 2. Now the recurrence relation is relatively straightforward. The index of each subsequent Fibonacci number is just 1 greater than the index of the previous number by the definition of index. So we can encode that into our recursive query here. Yep. And finally, we need to update our stop condition, the where clause. We want to filter on index instead of value. I'll update that. And there you have it. Let's try generating the first 15 Fibonacci numbers and run the query. All right, as you can see, we are almost there. It does appear we have some kind of off by 1 error here, since the sequence is starting at 1. And this is actually just an artifact of the way that this particular solution is designed, because 0 actually never gets to be n. It only ever appears as previous n. So selecting n as our final result, as we are here, will always leave off 0. So actually, we want to select previous n, and to compensate for shifting all the values back by 1, we actually also need to update the where clause to have a less than or equal sign instead of a plain less than sign. So let's run that. And voila, the first 15 Fibonacci numbers exactly matching our expectations. And just because it's always good to consider edge cases, we can check that this works even for the base cases. So let's try just getting the first Fibonacci number by updating this filter to 1. And as expected, it just returns 0. And let's just try it, the first 2 Fibonacci numbers to be safe. As expected, it returns 0 and 1. So yeah, I think this is a solid solution to our problem. It is by no means the only way to write this query. There are many different subtle variations on this, slightly different strategies for how to do the recursion, etc. But this is one of those variations. It gets the job done and illustrates the general approach of recursive SQL queries, and specifically generating Fibonacci numbers using SQL. Well, that's basically it for today's problem. As a fun little postscript, I do want to mention another equally valid but much less obvious way to solve this problem. It turns out that the Fibonacci sequence has what is called a closed form solution. In other words, a simple non-recursive formula capable of generating any member of the sequence in more or less constant time. This particular closed form solution is called Binet's formula. And as you can see, it is a fun bit of math that I sincerely hope no one would expect you to come up with yourself in an interview setting. I have prepared a SQL version of this calculation here. And we can see that it is capable of spitting out the nth Fibonacci number with no recursion at all, although this formula actually produces 0 indexed values, in other words, shifted by 1 compared to our solution above. For example, it considers 377 to be the 14th Fibonacci number instead of the 15th. All right, well, that is it for this video. Thank you for watching. If you have any further questions about this problem, or if you think of a different approach to the solution that I may not have considered, please let me know in the comments, and be sure to subscribe for more SQL query writing content in the future. Until next time, happy querying.